Hello, today we are back with a new episode of solid states physics, and here we are discussing about the a new condition in crystallography in addition to the condition called Bragg's law that we discussed in the earlier episode. The Bragg's law gives us some condition of the interlayer distance so that we can get a constructive interference and we can actually shine the light on the crystal and to see what kind of interference patterns and what kind of peaks that it is given, and we can infer something about the interlayer distances and thus the crystal structure. But how to connect this with reciprocal space formalism? So for that we will see another thing called Laue's condition. So this is what will actually be at the base of motivating the idea of reciprocal space formalism. For Laurent's condition, it is a more theoretical condition, which is saying that the transition between an electron from k to k prime momentum is given as 2 pi by h bar into k b k prime square delta e to the ek minus ek prime. So this is called the Fermi's golden rule. Fermi's golden rule. What is it stating? That an electron coming with a momentum k, hitting a crystal which has some potential V, and then it gets deflected, it gets scattered to another potential to another momentum k prime. And what is the probability or what is the rate that it is doing? This is given as this. So it is dependent on this normalization factor, and it is dependent on the matrix element of the potential between k and k prime. That is obviously from quantum mechanical rules. This is like quantum mechanical origin, and this is basically saying energy conservation. Energy conservation due to what? Due to this is considered as an elastic collision. So this is called Fermi's golden rule. Now we will see how we will get some condition out of it. So let us consider this thing called k vk prime. What is k? K is just a Fourier transform version e to the power k dot r x. Sorry, r. This is what k is. So if we do that, then what we will get? We will get this dr prime e to the power minus k dot r e to the power k prime dot r prime r v r prime. So this is the Fourier transform version. Now let us not look at this. So I will write it in a side note. On the side note. Uh, okay. So what I'm trying to say is that when we have this, then this potential is local. It means that it will have V of r delta r minus r prime. Until and unless r and r prime are not the same, V is not going to work. Basically, it's not going to take electron from one side and then like magically pop up, like make the electron pop up in another site. So that it can't do. So this is local. What it means that we get rid of one integral because of the delta function, and we have this, we have this ik prime r v r delta r prime r minus r prime dr prime. Due to this delta function, this dr prime will go away and this r prime here will be replaced by r. In, in the total, it will get k prime minus k dot r v of r. It is all over the space. All the space. R means all the space. Now, so we now know this matrix element. So the scattering amplitude is actually the squared of the modulus of this matrix element. So now we have to see something. So this is true for any material. This is true for any material. Any material. But now we will leverage the periodicity of the material. We will say that this dr, this whole space, is nothing but the summation of lattice vectors and dx over a, not a whole, over a unit cell. So uh, part we just made the whole space divided into boxes of unit cell, and we are saying if you go from one box to another, you just take a lattice vector. You go from one box to another, and you sum up all the boxes. So what it becomes? It becomes integral. This matrix element, let's say vkk prime. I am saying it becomes dx summation r x is in a unit cell dx vx plus r e to the power minus I k prime minus k dot x plus r. So we know v of x plus r is just v of x because periodic, right? So we will have this dx vx e to the power I k minus k prime minus k dot x. This will be separated, and outside the integral we will have e to the power I k prime minus k dot r. So the r dependence is only in this part. So we can actually take the summation and we can put the summation here. So this is a phase actually, like this is kind of a phase which will be added to the this integral. But the interesting fact is we know that this equals to 0 until and unless k prime minus k is an integral multiple of 2 pi by mod r. So that is an interesting fact. And what we are trying to say is uh, this is actually what is going to motivate the reciprocal space. This is called the Laue condition, and we often actually denote it by n into g, or like it's a g, where g is given as some integral multiple of 2 pi by r. And this is exactly where the reciprocal lattice vector concepts comes in. This is called the Laue condition. This is a famous condition. And now we will see that what is the like relation between Laurent's condition and the Bragg's law in the next episode. And from there, we will have a holistic view on how this reciprocal lattice formalism was developed. So meet you in the next class. Till then, see you.